So welcome all to week 3 tutorial for the course Deep Learning. I'm Pintu Kumar. I'm a PhD student at IUR Bombay. The topics that I plan to cover today are related to week 3 content of the course and would broadly cover backpropagation. It would cover cross entropy and how do we use this for classification problems, especially multi-class classifications. And then there is a small section that I have included that was not there in the lecture. So we'll talk about different kind of activation functions that we have and what are the advantages and disadvantages related to that particular activation function that we'll do. In order to do that, we'll also have a brief recap, or we will have a brief look at vanishing and exploding gradient problem that we encounter in deep learning setup. So this is my plan for today. During the tutorial, like if you have any doubt at any point, feel free to unmute yourself and ask then and there. Or you can also type in the chat box. I'll be monitoring the chat box constantly. Okay. So we'll begin with a very small recap of what has been done in this course so far and what we have discussed. So till now, we discussed about perceptron, right? We started with a simple neuron and then we went to perceptron. From there, we went to a multiple network of perceptron that we called as multi-layer perceptron or MLP. And till last lecture, what we said is that if we have one single hidden layer with sufficient number of perceptron, we can estimate any continuous function to any desired accuracy. Okay. Now, today, what we are going to do is we are going to see how do we get parameters for this multi-layer perceptron. Okay. So your perceptron would look something like this. This is your input. Okay. And there would be a hidden layer and then some output layer. There can be multiple hidden layers too, that also we looked at. Okay. So something like this. Also, we talked about gradient descent method that can be used to find a minimum of a function. Okay. So we have weights over here associated with these connections that we are making. So today we are going to see how do we learn those weights from the data that is available with us. Okay. So another portion of recap is, let's say, okay. So yeah. When you have your output layer, along with your output layer, you have one more thing, that is loss function. This also we sort of discussed in last class. So you have a loss function. Please joining. Just a second. So we have a loss function associated with your model, and we want to minimize this loss function. This is what we did in last class. Okay. Now, how do we minimize? So we minimize by tuning in our parameters. Okay. Okay. What are the parameters for this neural network that I just stripped? It is all the weights as well as the bias that we have in the network. Okay. People are still joining, so I'm admitting them side by side. Yeah. So we want to tune the parameters, right? So what are those parameters that we want to tune? The parameters that we want to tune are these weights along with the bias that is available that we want to tune. Okay. So these are the parameters that we want to tune, and what is the method that we're going to adopt for it? The method that we are going to adapt for it is something that is known as gradient descent that we did in sufficient detail last time. Okay. So just a very small recap. What do we do with gradient descent? So if W is the set of vector of parameters that we want to find. Then we initialize this with W naught, okay, and then we keep on updating W naught by W naught minus some eta times gradient of loss function with respect to weights. This is what we are going to do. So what we are going to cover today is how do we calculate this gradient of your loss function with respect to the weights of your neural network, and that is given by an algorithm that is known as backpropagation. Okay. So this was recap. We'll begin with something that is called as backpropagation. Okay. So the main goal of backpropagation, as I mentioned just now, is that if you have a loss function, you want to find the gradient of the loss function with respect to the parameters that you have in the network. Okay. So we'll begin with a very simple perceptron. Then I'll try to derive this gradient for a chained network. Then we will see a more complex kind of a network. Okay. So I'll be more focused on what is the meaning of this gradient, why are we multiplying with these quantities. But I won't be writing out the exact closed form that was discussed in the lecture, because that is already in the lecture. I am just trying to explain you how do you reach to that point. Okay. So yeah, I'll begin. So this is a simple network that you have. Here you have your three inputs, x1, x2, and x3, along with weights w1, w2, w3, and a bias or a threshold that you called in terms of perceptron. Okay. And this perceptron does a two-step thing. What it would do is, it would aggregate these quantities, that is w1, x1, plus w2, x2, plus w3, x3, and to the end it will add a bias term b, and that would be the your part that would be evaluated by the summation sign that I have written. For the second part, this perceptron will pass it through a non-linear activation function that I'm representing by sigma right now. Okay, this can be your sigmoid function, but right now I'm talking about some generic activation function that I'm taking on top of this summation. Okay. Okay. So I'm representing this summation over here, whatever I've highlighted. This thing I'm representing by letter O. Okay. So letter O is the summation thing that we have. Okay. So I'm taking a vanilla loss. So this is just a least squared error. So this is a squared error that we have. Let's say the data point's original output is y, and our model is predicting y hat. So what is the loss function that we would have? Loss function would be y minus y hat square. Okay. From here on, I'll try to derive it by writing it so that things are more clear to you. Just give me. Yeah. Okay. So my loss function that I'm given is y minus y hat square. Okay, you can switch, that's the square. Okay, now what I want to do is, I want to find the, okay, so if I have to update this using gradient descent method, then I need to find the gradient of this L. Okay, and it should be with respect to W as well as B, right? So I should find out del L by del W1, del L by del W2. Okay, so there are three terms only right here, but there can be more terms. So let's say del L by del WK, and then one more term that we have to find is del L by del B. Okay, so this is the task that we have. Multiple people wants to join. Admit. Okay. Anybody has anything to say? I could hear some noise. Okay, fine. Okay. So for the simple network, uh, if you look, you might remember chain rule, right? So what used to happen in chain rule, let's say uh, if you have a function like f of g of h of x, okay, then what you used to do is, so let's say if we have to find f is a function of this form, which is a function of g, and g is further a function of h, and h is a function of x, okay. Then if you have to find, let's say del f by del x, then what was the formula for this that you did in your school? This was nothing but del f by del g into del g by uh, del h into del h by del x. Okay, this is what we used to do in order to find such a complex derivative. I can give you an example. I'll give you an example rather. Okay, so for example, let's consider a simple example where we have x square plus 2 whole square. Okay, so you can see it as that, let's say your uh, h of x is x square. Okay, this is not a very great example, but we can still see g of h is h plus 2, right? And again your f of g is g square. Okay, so if you compose all of this thing together, so you will get x square plus 2 whole square. uh, what I was saying was that when you take the derivative of your loss function with respect to weight in earlier layers, that is dependent on the derivative that you obtain from later layers. So you need not compute all the terms in derivatives, but you will reuse some of the terms when you calculate the gradients. That's why this method is called backpropagation, because we use the terms that we have obtained in later layers in the previous layers. Okay, this is the concept we had backpropagation. So we have seen how do we calculate partial derivatives right now for a simple neuron. Okay, so what we can try doing is we can also find it with respect to B. Okay, that should be easy. So let's say if we have del L by del B that we want to calculate, it should be simply uh, del L by del Y hat that we have again, del Y hat, then del Y hat by del O, and then del O by del B. Okay, we have already calculated these two terms, we'll reuse it. So this is 2y hat minus y into sigma dash O. And if you take derivative of O with respect to B now, so O is this term, this is summation over here. So if you take its derivative with respect to B, it's nothing but 1. Okay. So this is how we go about taking partial derivatives. Anybody has any doubt till this point? Now we will look at a more deeper network after this, and we will actually see what is backpropagation. But for that, you just need to be clear that you understand how this chain rule works. So how did we derive partial derivative with respect to weight for a single perceptron? Is that clear for everyone? Anybody has any doubt in that, you can ask, I'll be happy to clarify.
Sir, if there are multiple hidden layers and number of biases, so the biases will also have been summed similarly, weighted sum.
No. Okay, so if you have multiple layers, okay, for example, in this case, you have multiple biases, right? So this bias gets added to the output of this particular neuron only, okay? And the second bias will get added to this particular neuron only. So the bias won't get summed together, but they would get summed at a different layers only. So they won't
Okay.
get summed together. Okay. Okay. So
Sir, can you please repeat the process of background?
Repeat the.
Backpropagating the loss function.
Yeah, I'm going to backpropagation. Right now, I just did chain law, like how does chain law work for a single perceptron. There was no backpropagation over there. Now I'm going to backpropagation. Okay, so quickly let's dive into it. Okay. Yeah, Pranav Tiwari, you can speak uh, or you can
Sir,
start.
sorry to disturb, sir. Sir, I wanted to ask, sir, why are there multiple sessions going for the same course at the same time, sir? How can we join two of them, sir?
Okay, so these sessions are not your compulsory sessions. These are just to clear your doubts because there are large number of students. That's why there are multiple sessions for this course. It's your choice which session you want to join. So these won't be
Sir,
evaluated or anything, right?
can they not be at separate times, sir, without clashes?
See, it also gets very difficult for us to take separate time out because all these things have been fixed already. It won't be very useful for you also to attend four different sessions on same topic and clear your doubts, right? And on top of it, you are also doing the NPTEL videos. That those are the prime resources that also you are seeing. And then on top of it, if you spend more 4 hours just clearing your doubts, I don't think that would be useful for you also.
Okay, sir.
Okay, so yeah, you can join any one of them and clear your doubts. That is the main purpose of these kind of tutorials. Okay, so I'll go slow over here. Okay, this is how back propagation works. Okay, and if anybody has any doubt at any time, just please stop me then and there. Okay, first of all, I'll clear the notation. Right now, we have only one input, that is x1. We'll extend this later on. But for simplicity, for explaining, let's say there is only one input, that is x1. Okay. And the weight associated with this x1 is w naught, and there is a bias term b1. Okay. So, yeah, I'll, for the time being, just ignore whatever I'm highlighting in yellow. Just ignore whatever is written over there. Okay. Now, for the next layer also, we have only one neuron. So the weight going from this first, this is our input layer. Okay, sorry, this is not your input. This is your first hidden layer. So from first layer to second layer, the weight is W1 and the bias is D1. So this was your input layer. This is your X1. This is your input. These three are your hidden layers, and this is your output layer, right? Okay, so these are the weights and biases associated with every layer, and in every layer there are two operations being performed. One is weighted sum, okay, weighted sum, and then that weighted sum is being passed through a nonlinear activation function. Okay, for example, in the lecture you would have seen sigmoid activation or linear activation. We'll cover in detail what kind of activation functions you can use. Right now, this is some kind of non-linearity that we're introducing on top of our weighted sum. Okay. Okay. So now the value that we get after summing weighted sum is denoted by A1, and the value that we get after activation, or that is after passing it through non-linear function, is denoted by H1, over here by H3. Here also we'll have similar thing. This would be A2 and H2. Okay, I'll try to explicitly write. So what is A1? A1 over here is W naught X1 plus B naught. This is what my A1 is. I'm just taking the aggregation, and my H1 would be sigma A1. So I'm passing it through some nonlinear function. Okay. Similarly, you can write your A2 as this would be W1 times sigma, sorry, this should be W1 times H1 plus B1. Okay. And your H2 would be sigma of A2. This is how your forward propagation works in a neural network. Okay. So if you would had multiple inputs, things would have gone accordingly. Right now for one input, this is how your forward pass would look like. And similarly for the output layer also, I am denoting it by AL because this is the last layer. So this is W3 H3 plus B3, and your HL, that is the final output, is nothing but some activation on AL. Okay, and on top of it you will have some loss function. Okay, so your loss function is loss function can be defined as y minus HL square. Okay, and our role is to minimize this particular loss function. Okay, so I'll push these things down because we want to keep looking at this network. Okay, if required, we will bring this thing up again. Okay, so first thing that we should try to do is we should find the gradient of this loss function with respect to the weight. Then only we can update the weight. Okay, so what is gradient of L? Okay, so sorry, this is first thing that I want to. Yeah, hello. Okay, so I want to calculate partial derivative of L with respect to W3. Okay, so because this is the first thing that I can see over here, then we will propagate backwards. Okay, so what is del L by del W3? Okay, so this is again a simple application of chain rule. This is del L by what you are getting as output. So your loss function is y minus HL square. So loss is directly dependent on HL. Okay, so we should take its partial derivative with respect to HL, and then and then partial derivative of HL with respect to your W3. Okay, this is the first step that we are doing. Okay, further we can expand it as this is del HL and then del HL by del AL, because your HL is a function of AL. Okay, this is what we wrote. I'll just adjust my, yeah, right. And then again,
So please explain this derivation, sir. I can find the gradient of loss function with respect to the weights of the third layer. That is, and then the following derivations. I haven't joined. Sorry.
okay, so right now what I'm trying to do is I'm trying to find the gradient of loss function with respect to the weight of my third layer. Okay, so using the chain rule, what I can do is I can write it as derivative of L. So this is my final output that I have. My neural network is outputting HL as the final output, and I can directly put it in loss function, right? So my loss function is y minus HL whole square. Okay, so I can split this into two parts now. So this is what I wrote. I'll rewrite it. Okay. So what we can write it as, so this would be del L now with respect to del HL, and then we can take partial derivative of HL with respect to W3. Okay, I hope this much is clear, like whatever I've written in blue over here, is this much clear?
Yes, it's correct. It's clear.
Okay, so similarly, we extended this thing that HL is again a function of AL. AL is just the summation part that we are having. So that is just W3 into the output of previous layer plus whatever bias we have. Okay, so now we are taking, we are again splitting this second term. So this thing is getting split into two terms now. Okay, so this is now again del AL by del W3. Okay, now this del AL, this is my AL. AL is a direct function of W3. So here we should stop. Okay, so we can write an elaborate form here also. So what what is my del L by del HL? This would be 2 times y minus HL into minus 1, right? This is what it would look like. Somebody is joining. Okay. And what would be my second term look like? So this would be nothing but sigma dash of AL. So right now I'm not specifying what is my sigma. Right now I'm just writing sigma dash of AL. Okay.
Sir,
And then
the loss function, sir, the loss function is y predicted minus the true value of y, the
yeah,
whole square. Is it so? Then the value what we get is the predict y.
can you please repeat the last line?
Uh, Loss function is y predict minus y true,
Right
the
now
whole
I'm
square.
taking y true minus y. So this is just a square. We can adjust that thing. That would work fine.
But when you find the partial derivative, it will become negative. No?
I have multiplied it by minus 1. I think that is not very clearly visible. So this is the minus 1 that I have included over here.
Yeah, if I take it as y predict minus true of y, I'll get only 1, not minus 1. The
No,
value will
so
become positive.
okay, so we can multiply this minus 1 over here and then we will get predict minus 2. That's the same thing, right? That's just
Okay then. Okay then.
right. This is again sigma dash of AL. And the last term is, this is W3H3, so last term is H3. So one important thing over here is that when you look at this derivative, this is just the first derivative that we have found out. It has the term H3 in it. Okay. So how do you obtain H3? H3 can be obtained via forward pass only. Okay. So if you pass your data point through this network, you obtain all these values A1, H1, A2, H2, A3, H3, and you save it. This one process is called forward pass. So before starting your backward propagation, you should do a forward pass so that you have all these values available with you, so that you can put it in the like this calculation of your gradient, and you can calculate the gradient. Okay, so this is one point. So before backward pass, you should do a forward pass. Okay, this is one thing. And this is what we have obtained for partial derivative with respect to W3. Now we will, yeah, hello.
Yeah. So we have only one weight, that is AL.
Right now we have only
Sigma.
one weight, that is W3.
Okay. If we have more than one.
We'll see that example. Right now I'm just trying to
Okay.
explain
Okay.
backward propagation. That's why I have not gone into multiple ways. Then we'll have a summation term similar to what was done in course. We will have a look at it. Okay. So now the second term that we are, so similarly you can also calculate partial derivative with respect to B3, but I'm skipping it because this is very similar. I'll straight away go to partial derivative of L with respect to W2. Okay. Now we'll start in the same manner the way we started for W3. So we have to reach till W2. So W2 is this point. We have to reach from here to here. Okay. So let's see how we can reach. So we'll see what path we can travel. Okay. So from loss function, you will again have del L by del HL, and then del HL by del W2 this time. Okay. This can be further again broken down into, I'll straight away write what it can be broken down into. Now del HL is a function of del AL, sorry AL. So, and then del AL is a function of H3, right? So it will have a partial derivative with respect to H3. Then H3 has a partial derivative with respect to A3. And from A3, we can straight away reach to W2. Okay. Now, if you see, there are some terms that are common in both of them. So one is this. Okay. I'll just increase the width here. One is this, right? So if you see this term over here and the first two term over here are same. Okay, so that's why this is a sort of called backpropagation, because in the next term you are using whatever you obtained in your previous term. When you will calculate this del L by del W1, you will have all these four terms common. Okay, so you can use these four terms, that whatever you have calculated as it is, and then calculate the next thing. Okay, so now we can also try to explicitly write this thing. Okay, so just a second. Yeah, so from above calculation we already know what are these first two terms. This is 2 times predicted minus actual times sigma dash at AL. Now this is del AL by del H3. What is my del AL by del H3? This is W3. Okay, so this calculation is not very hard. This is straightforward. Now del H3 by del A3 is sigma dash at A3, and the last term is del A3 by del W2, that is my H2. Okay, again we have H2, we should have obtained this via forward pass. Okay, so yeah, this is the basic idea of backpropagation, how this thing works. I am not writing all these things in closed form because that is already there in lecture. Those closed forms becomes very important when you train your model from scratch. Okay, then you can use those matrix notation to calculate your gradients and those kind of things. So those things becomes important over there. But to understand how backpropagation works, this is how it actually works. So you keep on going backwards in the chain to obtain your values. Okay, I can yeah,
The nonlinear
the sigmas are nonlinear functions.
functions used in all the hidden layers, but if, they will not have any effect in the backward pass. Is it? Because the gradient only we are propagating backwards.
Okay, so when you are propagating backwards, there are two things that are happening. If I understood your question correctly, I'm not sure if I understood, but I will try to explain, then you tell me if you got your answer. So we have these terms H2, H3 in the gradient calculation. These H2 and H3 are calculated by passing your A2 or A3 via your nonlinear activation function. So implicitly you are having your term passed through activation function even in your gradient. One thing is this. Not only that, you also have partial derivative of your activation function in your gradient. So there is an impact of activation function that you are taking care of while calculating the gradient. Was this like this was your question, or was it something else?
I couldn't. I mean, I couldn't express my question properly. So, given the model, it has been clearly specified that the activation function is non-linear in all the hidden layers, and the output layer is, it is a linear function.
Okay, so it is
No activation function is used in the output layer. It is mentioned in this way.
okay.
So the net value becomes the out value.
So the summation value would become the output value. So
Yes. So
yeah. Please complete.
So we haven't applied the activation function at the output layer for finding the output.
Okay.
It has been given that the loss function is the function what you are using, the squared loss.
Okay.
So the loss is calculated, and we are propagating backwards towards to find the updation of weights in each and every layer.
Okay. So in the hidden layers, there is some activation. There you are not considering the linear thing, or there also you are considering the linear thing.
the activation function is non-linear in all the hidden layers, and it is not applicable in the output layer.
Okay, so what would happen in that case is, so what you are saying is the HL that you are getting is nothing but your AL. So there is no activation at this layer, but this is just your like whatever you obtained by summation, this is what you get. So you can still do this thing by two methods. I'll suggest you like if you look mathematically, then this term over here that I'm circling now, that is del HL by del AL, this term would become 1. That's what we can see
Yes.
using mathematical calculation. But when you are implementing it, right, there what you can do is like if somebody says that there is no activation function, then you can consider something that is called as linear activation. I'll change the color of my pen. You should consider something as linear activation. Okay. So linear activation is nothing but your sigma of x is nothing but your x. If you do this way, then you need not change your framework of your code. So like if somebody asks you not to apply anything, then you apply linear activation and you include it in this form only. Its derivative would be 1 only over there because this is sigma of x is equal to x. So sigma dash x would be 1. And then implementation wise your life becomes easier in this way, but mathematically this term would vanish because this would be 1 and other terms would remain intact. This would happen in the case that you mentioned.
Thank you, and I'll try this and try to implement and find the answer.
For implementation, this thing would be much easier because let's say you wrote a generic code where your layers are something, okay, and you just define a function that is linear in nature and you define derivative that is 1. Then even though your derivative term is included in the calculation in your code, your term would be just multiplied by 1. That would make no difference to it. Okay. 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 So any doubt in like how this backpropagation worked? How did we find the derivative of L with respect to the W2 parameter? Then we will go to a multiple network kind of a thing so that we completely understand this backpropagation thing. Okay, so yeah, okay. So before going there, this you might have done in the course itself, but I will just try to repeat because this is a good motivation. Let's say your y1 is given to be x square, okay, and y2 is given to be x cube, okay, and z is given to be y1 into y2, okay, and somebody asks you to find del z by del x. How do you go about it? So the chain rule says that you should take del z by del 1 and del 1 del y1 by del x plus there is a plus term because your z is dependent on two variables. So this is del x. Okay. So you get something like this. If you draw the computation graph of this kind of a problem, how would this look like? I'll just try to draw a computation graph for this. So yeah, so this is your x, okay, there is a y1, there is a y2, there is a y2. So from here you are going here via x square, here to here via x cube, okay, and then finally they both are connected to another circle, okay, and this is your y1 into y2. So what you are trying to do is you are trying to find the derivative of this A lot of technical issues today. So we are trying to find the partial derivative of this particular node with respect to this node. Okay. So if you try to do that, you look at all the branches through which you can reach from here to here. Okay. And then you take sum of all these branches. Okay. So this is what I wanted to say over here. Now we will use a similar thing what we just talked about in a neural network. Okay. So right now also again I have restricted myself to one input for understanding purpose. Okay. And yeah, just give me a second. I am not able to change the color of my pen. 2-3 times this thing has happened today. Yeah. So now in this question, our main goal would be to obtain loss, derivative of loss with respect to the first weight that we have, that is del W naught. Okay, this is what we plan. Okay, so yes, we'll do that thing. So for that thing to be true, let's first start from these layers. Okay, and we'll try to find the derivative. Again, the loss function that we are considering is nothing but y minus hl whole square. Okay, so this is the simple loss function that we are considering. We'll go to classification loss in the second half of the lecture. We'll just finish this quickly. Okay, so what is my del L by del W21? So again, the setup is very similar to the previous question. You have some input. It would be aggregated with its weight. That thing we will call as A. So A11 means first hidden layer and first neuron, and its activated form is called as H, similar to the previous one. And then there is a second hidden layer where you have A21, A22, H22 and H21, similar to that thing. And then we have one output layer over here. Okay. So in this second hidden layer has two perceptrons rather than one in the previous example. This is the only difference over here. Okay. So what is my del L by del W21? I'll just quickly do this because we have done this previously. So this is just del L by del HL, del HL by del AL. Now del AL is directly related to W21. So this is del AL by del W21. Okay, this is what we would obtain for del L by del W21. Similarly, we can write del L by del W22. So W22 is this particular term. So again, this is del L by del HL into del HL by del AL into del AL by del W22. Okay. Now, next task is to find, I'll use different pen. Yeah. Next task is to find del L by del W11. Okay, this is what I want to find. Now, if you see W11, this is the path we should follow, right? This is the path. It is not dependent on W22. So in no term that would involve W22 or this A22 or this thing will have W11. So the only terms that will have W11 in future is this A21, H21 and this AL and HL. Okay, so this is the path that we're going to follow. So this is carefully have a look. If you don't understand this, please let me know. So this would be del L, similar to previous thing, del L by del HL, del HL by del AL into del AL by del H21 into del H21 by del A21 into, now A21 is directly dependent on W11, so del A21 by del W11. Is this thing clear? Why did we obtain this thing? Any doubt, like I would ask, any doubt in how did we obtain del L by W11? So you can see that these two terms are again common. So if you have calculated it in above example, you can still use it. If you have calculated in upper layer, you can use this thing. Okay. Okay. So similarly, the way we defined del L by del W11, we can define del L by del W12. And this is very similar to this. This is del L by del HL into del HL by del AL into del AL by, now this is H22 and del H22 by del A22 into del A22 by del W2. Okay. Sorry, W12. This is W12. So we have reached till this point. So we have calculated the gradients with respect to up to this point. And this is very similar to what we have done in chain. Now only we have two chains right now that we have obtained. Now main task is to combine these two chains. Okay. Now what we will do is, we will see del L by del W naught. Okay. So the main thing that we wanted to do is, this is del L by del W naught. So you can see that there are two paths via which W naught travels to the loss. So one is this path and another one is this path. So we should take both these paths sum, similar to what we did over here. So there were two paths via which X was traveling to Z via Y1 and Y2. So we took their sum in the partial derivative. Similar thing we will do over here also. Okay. So yeah. So this is okay. So we'll start and then see what happens. Okay. We'll start. So this is del L by del HL and then this is del HL by del W naught. Okay. Okay. So let me write one more thing. So this is del HL by del AL and then del AL by del W naught. So till now we haven't branched. Reason is we reached from loss to HL, then HL to AL. Now there are two branches that are opening up. Okay, that would lead to W naught, right? So this particular term that I'm highlighting by yellow, this would specifically split into two terms. So we can write that thing as, so the first two terms would remain again same. And then there is a two terms that would be jointly multiplied. And those two terms are, okay. So this would be, just see what I'm writing makes sense. So this would be AL by del H21, then del H21 by del A21, then del yeah, A21 with respect to del H11 and then del H11 with respect to del W1. Again, there is a summation over here. So I'll just write and pause. Del AL, del H22 into del H22 by del A22 into del A22 by del H11 and then del H11 by del W1. Does this thing make sense to you? like any doubt that you have related to this? So because there were two paths similar to what we drew in this graph, so we took the partial derivative and summed it up along both the paths. Okay. So here is the summation. One going via upward path and one going via the downward path. Okay. So this is how back propagation works. I haven't written the closed form, but I have given you all the ingredients that is required to write the closed form. So I've given you, like, if it is in a chain, how do we process the gradient? If it is two layers combining at one place, how do you process? So if it would have been three or more layers combining over here, then there would have been more terms in summation. So it would have been summation along the third path also, summation along the first path also. Okay. Any doubt in this before I can proceed?
Sir, this H11 is the H naught according to your diagram.
I haven't defined any H naught, but yeah, according to what notion, I think, sorry, this is the H naught. So this is the
Okay,
output of the first layer.
okay.
This is it. Okay, so I will upload this sheet that we have over here. Okay, so I have included a link over here. So in this link, there is a solved example of, so there is two inputs, one hidden layer with two neurons and one output. So there is a numerical solution sort of in form of example, what values will you obtain, what will you get. So I did felt that I would have enough time to solve it over here. So I've included this link. So you can access this link when I post this sheet. So I would highly recommend you to have a look at it, and if this back propagation is still not clear, it would be definitely clear by this solved example. Okay. Okay. So you can use this link. Yeah. So now just a recap. So now the question is, how do we learn neural network? So as I mentioned during our discussion also, the first thing that you should do is you should do a forward pass. Okay, because if you look at these derivatives, many of these derivatives, if you look at, for example, this thing would boil down to some a. Okay. Okay, so from here, what we solved, I'll motivate from there only. So we had H3 over here. Okay, we had AL values being used over here. So during calculation of gradient or back propagation, HKs and AIs are used. That's why you should first do a forward pass, obtain the values of AIs and HIs. Then you should do a backward pass to get the gradients. There you will use these values HIs and AIs, and then update the weight. So this is one epoch that you would do. Okay. So this is what you will do, and yeah. So this is what I wanted to say. Okay. So we can try some of the examples from previous year's assignment. So first question is this. Can you guys please try, and I'll wait for 1 or 2 minutes. This is a simple calculation of gradients. So you are given with a function in two variables, and you have been asked to calculate the gradient of this function. I'll wait for 1 or 2 minutes. You can. Okay, I'll quickly do this because this is not very useful. I have much more useful contents to cover. Okay, so del f is again del f by del x and del f by del y. So if you take partial derivative of this thing with respect to x, so you just treat y as some constant. So this would be y cos xy into cos xy square Yes. And then this would be, because this is cos, this would be minus sine. So this is minus, and then y square sine of xy square into sine xy. Okay. I think none of the options are correct. This should be xy everywhere. Okay. So there is some mistake in the options that are given, but that's fine. So similarly, you can calculate with respect to y. So this would be x cos xy into cos xy square, and again minus. This is 2xy sine of xy square into sine xy. This was just partial derivative, so I won't utilize much time on it. Let's go to the next question. Okay. So read the question. The question says, answer the following question with respect to feed-forward neural network given below for a classification problem. Okay, so this is a classification problem that someone is trying to do. So yellow nodes represent bias. So this is all the bias. They have combined it to form something called as H node or H node 1, H node 2. So rather than writing B1, B2, B3, they have combined it as a node and written it over there. So this would have many terms so in it, just remember that. So this is the output layer and these are the hidden layers. So first question is, how many bias parameters are needed to learn our network? So you need to find how many bias are there in the network. Okay, so you just need to count the actual number of perceptrons that you have. So in the first layer you have 3 perceptrons, that is x1, x2 and x3, and this x naught, I think Sudha that is correct. So this x naught is just a bias term. So how many bias terms would be there? That is equal to the number of element in the next layer. So x naught has 8 biases. Similarly, h naught a has 8 and this h naught 2 has 3 biases. So total number of bias terms is 8 plus 8 plus 3, that is 19. That is correct. Okay. Now next question is, how many weight parameters are there that need to be learned? So this question is specifically with respect to weight parameters. You need not count bias. So you just need to tell how many weight parameters are there. So input layer has 3 and this second layer has 8. So there are 24 connections over here. This is 8 cross 8. There are 64 here. Then 8 cross 3. So this is 24 plus 64 plus 24. So this is 2. This should be 1112. Yeah, somebody got there. So there are 1112 parameters that need to be learned. I felt that this year's question were slightly better. Last year I didn't found many good questions to include in this thing. But yeah, this is what we have right now. Okay. So, okay. So the question is, which of the following steps in proper order constitute to training of a feed-forward neural network? This is what I just discussed. Can you please, guys, tell me what should be the proper order in which one should learn from a neural network? Should he do a backward pass first or a forward pass first, or should he update his weight first? So the first step that he should do is a forward pass. Again, why? Because you need values of your AIs and HIs. Okay. Then he should do backward pass. Why should he do backward pass? To obtain gradients. And then he can do weight update. Okay, so forward, then backward, and then weight updates. This is the correct answer. And this is how one learns using a neural network. Okay. Which of the following statement is true? Can you please answer this one? I'll wait for a minute. What is the use of backpropagation? Yeah, this is used to optimize the weight of a neural network. Right, correct. So, okay, so backprop is used to optimize the weight, that is correct. What is used to compute the output of a neural network? So what should be, like, if there is, this is sort of match the correct answer kind of a thing that we used to do in school, what should be the answer for this? It is used to compute the output of a neural network. What is this called? This is called
Loss function.
forward pass. Right. Loss function is the not, I won't say the output layer in some senses, but yeah, this should be forward pass. The second thing, it is used to initialize the weight. This is just initialization. And last one is regularization. That also we would do somewhere. Okay. 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 So yeah. Okay. So this was about backpropagation that I had in plan. Okay. So there is one link that you should definitely check out that I have included over here. And now we would slowly move to something else that was covered this week. That was entropy, cross entropy. One extra thing that I've included from my side is KL divergence. The reason is I like to see cross entropy as a subpart of KL divergence rather than it being an extension of entropy. I feel this is more intuitive in nature. So we will talk about this very briefly. Okay. So yeah. So this portion is also going to be slightly brief today. Okay. So first term that we encounter is something that is called as entropy. So entropy, okay. Okay, so for example, right now I'm in Maharashtra. So let's say somebody says that uh, tomorrow the temperature is gonna remain something between 16 degree to 24 degree. Okay, so and on some other day, so this is information 1, let's say this is I1, this is I2, and somebody says that tomorrow is gonna snow in let's say Mumbai. Snow in Mumbai. So this is the usual temperature that people would expect in Maharashtra, right? So if somebody gives me this information, right, this doesn't carry much value for me because whatever he's saying, I sort of already know. Why do I already know? Because this is a high probability event. This is like usual whatever happens. So high probability event means usually what would happen. So if somebody gives me this information, this is not of much use to me. Okay, but if somebody says that it is going to snow tomorrow, then I'll probably look for my winter clothes and I'll get ready for that. So if somebody tells me something about a low probability event, then that particular information carries more value or more information to me. Okay, so this is one thing. Okay, so yeah, just a second. So what is entropy? Entropy is sort of expected amount of information that a particular I would say probability distribution carry. Okay, so let's say this is information I that happens with probability p. Okay, and what we want to do is that if I have higher probability, then the information should be low, or if I have lower probability, the information should be high in this. So this can be replicated by saying that if 1 by p is high, that means p is low, then my info should be high, right? And if 1 by p is less, then my info should be less. Okay, and then sort of to we sort of like scale it via log. So information is given by something like log of 1 by p that a particular event carry. So that is given by log 1 minus log p. Okay, so this term is 0, so this is minus log p. So minus log p of a event is the information that particular event carries. So extra information that particular event gives you is captured by minus log p. And if you take the expected value of that thing, that is given by this thing. So this is minus pi log pi. So if you have some random variable x, which take values xi with some probability pi's, then the entropy is given something like this. Okay, so this entropy is not of much use in deep learning setup, but we study it because cross entropy is sort of a very natural extension to it. Okay, so what is cross entropy? Okay, so cross entropy has two terms, P and Q, and then these P and Q you should remember in the same order. Okay, so let's say the data set that you have, so data of that particular set is obtained from some particular distribution P. Okay, let's say. So for example, what happens in classification? Okay, we'll go to that later on. So let's say you have some true distribution P that you are trying to estimate with Q. Okay, then the amount of error that you are making is given by cross entropy. Okay, so that cross entropy is given by minus pi log of qi. So entropy looked something like minus pi log pi, but now this pi has been changed by qi. Just remember one thing, that whatever comes inside this log thing is your estimated distribution and not your true distribution. Okay, so if you just change the role of p and q, so you should see that this pi log qi is not equal to summation qi log pi. So these two are two different terms. That's why you should remember where you should put your estimated distribution. Okay, so I'll get back to cross entropy, but via this route of scale divergence. Okay. Okay, so just a small pause I'll take, and then okay, let's continue. So what is scale divergence? Like if you have done some maths course or something, you might know that if you want to find a difference between those two things, the best thing that you go for is the distance between those two things. So let's say you want to compare two values, let's say 2 and 3. So how much gap is there? To compare that, you find distance between 2 and 3. You can do 2 minus 3 mod or something like that. Okay. For example, if you have two-dimensional plane, the distance between these 2 points gives you how far apart these 2 points are. Similarly, what people tried to do was, if you have a probability distribution, let's say P, okay, and you have some probability distribution Q, people tried to find out how close is P to Q. Okay, in order to do so, they find something known as scale divergence. Okay, so again, your P is your true distribution, and you are trying to estimate P via your Q, and then you want to check how close have I reached to P. Okay, so if you look at it carefully, so if your Pi is equal to Qi, then what would happen to this particular term over here? So this term would become 1, right? So if the term inside log this thing becomes 1, then overall you would get a value of 0. So if your P is exactly same as Q, then your KL divergence is 0. Okay. Another thing is that okay, then your KL divergence becomes 0. Okay, one thing is this. But one thing I want to make very clear is that this is not exactly a metric. This is a divergence that people say. Okay. So why is this not a metric? If somebody is here from math background or have heard of metric spaces, I would like to say this is not a metric because this is not symmetric in nature. So what does that mean is that D of KL, P given Q, is not equal to D of KL, Q given P. So KL divergence between P and Q and P are not same. That's why they are not metric. This is for somebody who has done matrix spaces. If somebody has not done, just you can ignore. Okay. Okay. So KL divergence is defined in this way, the way I have written over here. That is Pi log of Pi by Qi. And one thing is very clear from here. If my P is equal to Q, then my KL divergence is 0. Okay. Okay. And so is the, so what we want to do is, when we do classification or if we define this loss function, let's say your P is some true distribution and you want to estimate Q, what you want is your Q should be as close as your P. Okay. So what you want to do is you want to minimize your KL divergence. Okay. So we will reach from KL divergence to entropy. So what is your KL divergence? This is summation Pi log Pi by Qi. Okay. If you just split this log thing, what would it become? This would be summation Pi log Pi minus Pi log Qi. Okay. Now, just let's take a small step back and let's analyze what we have done. Okay. So what were we trying to do is, we had some true distribution P, or if you talk in terms of deep learning model, you have some true labels Y, right, or true output Y available with you. You want to model in such a way that the Q that you are obtaining should be as close as you want to P. Okay, this is what your aim is, that my P should be as close as your Q should be as close as your P. Okay, so P is a true distribution that you can't change. Okay, if you want to minimize the scale divergence, then your Pi log Pi, this term will always remain constant because P is the true distribution and you can't change it. Okay, so the only term that you can optimize is this thing. So minimize this thing is similar to minimizing this particular thing, Pi log Qi. Okay, so this is nothing but your cross entropy. That's why I said I want to motivate it via KL divergence. Okay, so what would happen? What we said is, like when your P is equal to Q, then your KL divergence is 0. Okay, so that is the minimum value that you obtain for your KL divergence. That's why when you minimize this particular thing, you will get minimum value at P is equal to Q. Okay, so when your P and Q distributions matches exactly, then you will get least value for cross entropy. So we treat cross entropy as a loss function for our classification problem. Is this thing clear? Any doubt till this point? So like from a use case, if you just forget the maths, the takeaway is you can use cross entropy as a loss function for a classification problem, and the formula for your cross entropy is given by this thing. Okay, where your Qi is the predicted distribution and Pi is your true distribution. Like even if you didn't understand a lot, this thing you should at least remember and understand, right? That this is a loss function that people define on classification problem, and Pi is your true distribution and Qi is your predicted distribution. Okay. Okay. So I said that we can use it as a loss for classification, but how do we use it? We will see it now. Okay, I won't try to rush much. Okay. So what happens in classification? I'll go for straight away for multi-class classification. You can just reduce it to binary on your own. I'm sure you will be able to do. Okay, so let's say you have some data set xi, yi. You have some data set where xi is some feature. Let's say xi belongs to R3, for example, and your yi also belongs to R3. So you want to predict whether, so you are given some let's say image, that won't be R3, but let's say you are given some image, you want to predict whether it's cat, dog, or elephant. Okay, this is the prediction that you want to make using your deep learning model. Okay, so how would your neural network look like? So it will have 3 inputs because this is R3. Then it will have some hidden layer, and there would be connections between these. Okay. Okay, and then there would be 3 output layers. Okay. Okay. So this is something how your neural network would look like. Okay. So you have some input. Okay. Some output, some hidden, and some output. Now in classification, what we try to do is, for this output layer, what we want is that this my first output perceptron should tell me the probability that my input, whatever I have given, is a cat. So, okay, so I should write it more carefully. So, what is the probability that my y is cat given whatever input I have? This is what I want from my first output. Second one should give me the probability that what is the probability that my image is of a dog given whatever input I have given. Similarly, this one is that it is elephant given x. Okay. So, to convert this final output to these probabilities, we use a special kind of activation function that is known as softmax activation. Okay. So, let's say in the language that we were talking before, this is my AL1, this is AL2, this is AL3. Now, if you remember, AL1, AL2, AL3 will be passed through sigmas to obtain some HL. Okay. So, what is the sigma that we should use so that this quantity is converted into a probability distribution? This is what we are going to do. So, that activation function is called as softmax activation. Okay. So, what is softmax activation? So, softmax activation is nothing but e to the power ai. So, this is sigma, yeah, this is, let's say this is sigma of ai. One more thing that I want to mention over here is all these activation functions that we do on some layer, those act element wise, right? So, over here you can say that al is your vector of al1, al2, al3. Sorry, I should be more careful about my handwriting. Yeah, if you have al something like this, then sigma of al would mean that this is just sigma of al1, sigma of al2, and sigma of al3. This is what I mean when we say that it should act element wise. Okay. So this is this by summation over all. Okay, so I is equal to k to 1 to k e to the power a. This should be some other variable a. So what we actually do is, let's say if you want to calculate the value for this first one, you take that particular thing in the numerator and take sum of all of them in the denominator, and you will get softmax activation. Okay. So this is something that we use. So, okay. Any doubt in softmax activation? Okay. Either I am making everything clear or nothing. I'm making nothing clear. Okay. So, yeah.
Can you repeat the calculation, sir?
Calculation for softmax.
Yeah.
Okay, so I'll give you an example. So let's say in the final layer, I got this as output. Let's say 2, 3, and 1. Okay. So the final layer, here I got 2, here I got 3, here I got after summation. So what would softmax do is, so it will do, so this, let's say this is HL1, this would do e to the power 3 divided by e to the power 1 is, sorry, 3 plus e to the power 2. Okay, I am making a mistake. Okay, so the first element is 2, so this is e to the power 2 plus e to the power 2 plus e to the power 3 plus e to the power 1. This would be my first element, that would be that I would get after activation. So this is what I would get after. This is HL1. Second element would be e to the power 3 by e to the power 2 plus e to the power 3 plus e to the power 1. And similarly you can obtain. This is how softmax works. Okay, this is how you can. So in any application, if your final output layer demands an probability distribution, then in the output layer you should try using softmax activation. Okay.
Thank you.
Okay. So one more thing that I would cover later, but I want to just mention, because there is a summation term in the denominator, this activation function is computationally expensive. So people sort of use some approximations to it, and people have tried using approximation to it using other methods. That I think there is a week on word2vec, there we would see. Okay. Okay. So we wanted to try to use this cross entropy for as a loss for classification problem. Right. So what we have obtained is, we have obtained some Q now, which is a probability distribution. So this is a predicted probability distribution. How did we obtain this? By passing whatever output I had via softmax activation, right? So I have obtained output in form of a probability, but to use cross entropy, I should also have my what I should say that yeah. So I should have my true labels also in form of probability distribution, right? So let's say some y is cat. Okay, what we can do is, so we can construct a vector where first position is corresponding to cat, second position is corresponding to dog, third position is corresponding to elephant. So whatever is the output, we can place a 1 over there and 0 otherwise. Okay. So this is what we can do to convert, like if your existing data has only one label given to it, you can convert it in form of a vector, and this vector is called one hot encoding. Okay. So now you have at both the places you have a probability distribution P and Q. So then you can use your cross entropy to define a loss and use it for classification. And still, like even today, this cross entropy is most popular loss function for classification problem, especially multi-class and multi-level classification problem. Okay. Okay. So we will solve some questions based on it. We'll quickly do, and then I'll cover some important activation functions, their advantages and disadvantages. Okay. So this is the question. Question says we have a multi-classification problem that we decide to solve by training a feed-forward neural network. What activation function should we use in the output layer to get the best results? Okay, so what do you guys think is the answer? There are 4 options given: softmax, logistic, 0, 1 and linear. Yeah, so softmax is the correct answer that we discussed. So logistic is useful for binary setup, and this is much useful for multi-classification. This is not a activation function at all. 0, 1, it can be treated as an activation function, but generally we treat it as a loss function. Linear is not applicable for classification. Okay. So second question is, which loss and activation function for the output layer is best suited for the above given network? Okay. So the network that I'm talking about is this question that we did. So this is the question where your output layer has 3 vectors, that means that the person is trying to do multi-class classification. That's why you have more than two output network. So let's get back to the question. Now the question asks, what is the best pair of loss and activation function? So we just did this thing also. So we can use cross entropy along with softmax that you guys told me. So this is the best fit. Okay. Okay, so this is related to entropy and those kind of things that we did. So we are given with an event A that is happening with 0.85 probability. And the probability of event B happening is 0.05. Okay, which of the following statement is true? Okay, so remember the rule, higher the probability, high probability implies low information content. Okay, so event A has high information content. A has higher probability, right? So A should have low information content. So this option is correct. Now B has low probability. So B should have high information content. So these two options are correct options over here. Yeah, C and D are correct. Okay, I should give some time for you guys to solve problem. Okay, so for this I'll give you 2 minutes to think. Then it would be more useful. You can see the question, I hope. Okay. Let other also try. So let y be the true distribution, a true class label, and P is the predicted probability of the true class label in the binary classification set. What is the following correct for binary cross entropy? So cross entropy is given by summation Pi log Qi. Okay. So where P is your true and Q is your predicted. So now we have only two classes. So this same thing would happen. So true probability is y. So this is minus y log P. P is your predicted. And there is one more term. For the second class, what is the probability? This is 1 minus y log of 1 minus p. So this second option is correct option, as mentioned, right? Like anywhere, if you have doubt, please stop me. I'm under the impression that things are clear. That's why I'm stop. Okay. So the question is, can cross entropy loss be negative between two probability distribution? So this is the formula for cross entropy loss. Can you please tell me if it can be negative or not? Pi log Pi. Think about what happens to value of log when your x is less than 1. So log plot is something like this, I guess. Yeah. This is for 1, right? Right. Right. So when your Pi is less than equal to 1, then log Pi value is always, so this much value, this much is less than equal to 0. Okay. So there is a negative sign ahead of it. So the overall value would be always positive. So cross entropy between two things is always positive. Okay. Okay. So this is what we had for this week's content, whatever was covered in the lecture. Now I had something in mind that I thought would be useful for you guys, especially when you are implementing this kind of model. So I included some activation functions and their advantages and disadvantages. Okay. So first activation function is just your linear activation function. Okay. So phi of x is just phi. I am denoting activation function by phi. So phi of x is just x, that is your linear activation function. In this case, you don't have much of non-linearity induced. So its advantages are that it is very simple. Its gradient is pretty simple. It is just one. Okay, so it's computation wise very simple, but because it is linear in nature, so it is not able to capture a lot of functions. Okay, so its expressibility is not that great. Okay, so and disadvantage is this. Second function is sigmoid that you have seen. So the activation is given by phi of x is equal to 1 plus uh, e to the power minus 1 divided by 1 plus e to the power minus x. Okay. So everywhere, whatever is there in blue, that is graph of your function. And what I have drawn in purple is your graph of derivative of that particular function. Okay. So one phenomena that I want to say, I'll just quickly go back. Okay. Okay. Can you guys please look at this del L by del W naught? Okay. So in this term, just a second. Just give me a second. You see over here, wherever we have term like del H by del A, that thing is replaced by sigma dash at that point, and that where sigma is your activation function. Okay. So over here also we have this term at many places. One is this, so this would be sigma dash, and this would be sigma dash, and this would be sigma dash. So there are three places where we could see sigma dash term. Okay, and this is very simple rudimentary network that we have. Only one input, two hidden layers where one of them had only two elements. So when we have even a good size network, there are a lot of sigma dash that are being multiplied with each other. Okay, one thing is this, that there at many places there are these sigma dash that get multiplied with each other. Okay, where sigma dash would mean activation in first layer, then in second layer, then in third layer. So these things gets multiplied while calculating the gradient. Now, if the value of gradient is very low, for example, let's say if my sigma dash is small, okay, for example, I'll just motivate this, not much I'll do here. Okay, let's say my sigma dash values that I'm getting is something between 0 to 0.5. Okay, and if you multiply 5 of them, okay, then for example sigma dash into sigma dash into sigma dash, the value that you will get would be very small. Okay, so if derivative is small, then because these things are getting multiplied in gradient, the final value of gradient that you will get would be very small. Okay, so because the gradient is very small, then you will making very less update in your weights. Okay, so that's why you will take very large time to converge, or even in some cases you won't converge even after very large time. Okay, because the gradient steps became very small in this case. So this kind of phenomena is something that is called as vanishing gradient problem. Okay, how would we overcome this? These things I think would be covered in later lectures. Right now I just want to say you that this phenomena is called vanishing gradient problem. Okay, another thing that is similar to this thing is, let's say the sigma dash value is large, then large quantities getting multiplied with each other would mean that your gradient value becomes very large. Okay, and that phenomena is called as exploding gradient problem. Okay, so this is the two things that I wanted to just mention right now. We will see these things in later lectures. Right now I just wanted to mention. Okay, so this is our sigmoid activation function that you have used for binary classification during perceptron and those kind of things. So we'll look at some of its advantages and disadvantages. Okay, so its advantage is that this function is differentiable everywhere. So if you look at the curve, this is very smooth. So when we calculate the gradient and those kind of things, so it is differentiable everywhere, and it is normalized between 0 to 1. So for binary classification, if we just output one perceptron with this particular kind of activation function, we will get our answer. Okay, so because it is normalized between 0 to 1, this is very useful for binary classification. Yeah, this is what it is written, useful in binary classification. Now it has some of the disadvantages. First thing is, if you look at its gradient, the maximum value it is obtaining is something around 0.3, 0.2 to 0.3. Okay, so the value of derivative is very small. So if you have a larger network, then it might suffer from vanishing gradient problem that I mentioned few moments ago. Okay. Okay, so one thing is that it is not a zero-centric function. I won't cover what is a zero-centric function right now because uh, okay, so what is a zero-centric function is, so the value of the function is sort of distributed on both sides of the x-axis. So if you look at this thing, the value always remains above the x-axis. So it is always positive output function. Okay. So a zero-centric function would mean that it has values on both sides of 0. It has positive values also, negative values also. So if you have functions that are only positive values, that restricts your like sort of the generalization power. I would say that you can't like, so if you have a function that is both positive and negative, that gives you a more search space. Right now I would say just this much. I think this topic is covered in later week. At that time we will see, but right now I just want to say that because this obtains just this has only positive values, this is one of its disadvantages. Okay. Another thing is that we have to calculate the exponential value, which is sort of computationally expensive. So we want to avoid going into exponential values. Okay. This was related to sigmoid function. I am sort of just skipping through it, but I'll upload this thing. So when you are using it, this might be useful to you. Okay. Okay. So something that is very similar to sigmoid is your tan h function. Okay. So whatever disadvantages we had in tan h, those things are sorry, in sigmoid, those things are taken care of by this tan h function. Now if you look, the derivative is also going to 1. So we have sort of avoided this vanishing gradient problem. And this function is zero-centric. So it takes values negative also, and it takes positive value also. Okay, so these are the two advantages. Disadvantage is that even though it is taking derivative values greater than what we obtained in sigmoid function, it is still less than 1. Okay, so less than 1 means that if you keep on multiplying, it would sort of again go to 0. So this is slightly higher value of gradient, but still suffers from gradient vanishing gradient problem. This is one of the disadvantages. Okay. Okay, so this sigmoid, what did I write? Yeah, sigmoid and tan h, these are mainly used for your binary classification problem. Okay, you can use it as activation for some hidden layers also based on your application, but this is what it is mainly used for. Okay, this is a very important activation function. This is called ReLU activation function, and this is sort of one of the most used activation function for hidden layers. Okay, to induce nonlinearity. How does the graph look like? This is maximum of x comma 0. Okay, so when your x is greater than 0, the value of function is x, that you can see via this blue line. When your value of x is less than 0, then the value is 0. So this blue line and purple line is overlapping, that's why you are not able to see, but there is a blue line over there also, which is extending over here. Okay, this is how a ReLU function looks like. Let's first talk about its disadvantages, then we will talk about its advantages. Okay, so first disadvantages is that it is again not zero-centric because the value it is taking is always above 0. So yeah, this is 0 on your y-axis. This line is just some fictitious line, ignore that thing. This is your 0 on y-axis, and the value that it is obtaining is always above that line. Okay, so there is one more problem that it has, that it is not differentiable at 0. So there is a sharp thing over here. So this is not differentiable at 0. Okay. Okay, so there is one more thing that is an important drawback of this thing, that is called as dying Rayleigh problem. So whenever your x is less than 0, it straight away gives value as 0. So the contribution of that particular node is gone, and that's why the weights associated with that would also not be updated. Okay, so this is one problem that happens with Rayleigh because of the 0 value. So what people do is they take very small value close to this and they try to append it on the negative half of it. We will see those kind of things also. Okay, so what are the advantages? That it is computationally very inexpensive. You just need to find whether it is x is greater than 0 or less than 0, and you will have value based on it. Okay, so this does not suffer from vanishing gradient, right? Because the derivative is 1 for the part where you are interested. Okay, so phi dash is always 1 when your x is greater than 0, and this is the part in which you are mostly interested in. Okay, so this is very useful in regression tasks, especially in intermediate or hidden layer. Okay, so an extension of Rayleigh is something known as leaky Rayleigh. To avoid dying Rayleigh problem, rather than taking value 0, what people do is people take a very small inclination, and that is a of x. That's take a would be negative over here. Okay, so the advantage is that it solves a dying Rayleigh problem, but the disadvantage is that now we have to learn one more parameter, a. Okay, so earlier we had 0 over here, so we have increased the number of parameters by 1, so we now need to learn one more hyperparameter, alpha or a in this case. Okay, okay, a won't be negative. I was wrong about it. Sorry. Okay, so last one is softmax activation that we just talked about. Softmax activation is e to the power zi by summation j from 1 to k e to the power zk. Okay, so this advantages are whatever we mentioned. It is used in last layer for multi-class classification. It is very useful over there. So it is useful to convert any value to probability distribution that you can have. The only disadvantage it has is it is very computationally expensive. So let's say if you want to look at MNIST data set where you have MNIST 1000 data set where you have many output classes, then the denominator calculation becomes computationally expensive. So this is one disadvantage that this thing has. Okay, so today we had a lot of content to cover, so I didn't include a Python code today also. I'm really sorry for that, but I've included a link where there is a step-by-step guide to implement a basic neural network using a PyTorch library. And this is a very basic kind of code where everything is explained. You can use this link to access that particular Python code. Okay, and they I think have used Rayleigh activation. You can try changing those activation functions and see how does your prediction change and those kind of things. That you guys can try. It would be useful for you. So this is what I had prepared today. So if you have any doubt